Hi, I'm Kathleen Almy. I'm the CEO of Almy Education, and I'm also an adjunct math professor at Rock Valley College. I'm going to teach you today how to write non-Googleable problems. So technology is evolving, it always has, and as it evolves, we have to adapt, just like we always have. So just like with graphing calculators, when they became something that was in our classrooms, we had to adjust how we wrote questions. The same is true for programs like Photomath or Wolfram Alpha, that we have to adjust how we write problems. Otherwise, we're just testing the ability, can the student use the program? So I call these problems non-Googleable problems, meaning problems that you can't just put into Google or some kind of electronic system like Wolfram Alpha or Photomath and it just provide the solution for you. So how do you write that? So here's an example of something that we did in my department years ago, but it gives you a sense of the idea of what we go for when we're trying to move away from something that the technology at one point it was a question, and then technology became to be, and it's really not much of a question anymore because the technology can do it. So in our stats classes, years ago we used handheld scientific calculators, and then we moved to graphing calculators. When we first changed, we realized that questions like this that we used before the graphing calculator, like find the equation of the trend line and the correlation coefficient for a given data set, that was actually something that the students had to work on to be able to do. With the graphing calculator, it was just, can you type that in? It really wasn't a task or anymore of their abilities. And then we would do things like use the line to predict. And we still do that. And that tested a little bit because that got a little bit more into being able to use what you get from the technology and not so much just can you get a certain function or equation or solution. So that kind of question we were able to continue to use. But finding the equation and the correlation coefficient, that's not much of a test when they have technology. So after the graphing calculator, we had to start thinking, first off, what do we want our students to be able to do? If finding the equation of the trend line is really, really easy, then what do I need them to be able to do instead? Because they're obviously going to have the equation very quickly. So we would ask things like, use technology to find the equation of the trend line and R, but those now are gimme questions. Those are easy. So the next step is, what does it mean? So we'd ask things like, interpret the slope, interpret the y-intercept. That wasn't something that we spent that much time on before because we really didn't have that much time. It took them so long just to even get the equation. Now they have it quickly. So what do we want to do with it? Well, we want to go deeper in our understanding. And we would ask things like, what are appropriate values to use for predictions? We can also ask them to use the line to predict, but it's also, what should we be using as numbers to input for predictions and what should we not? And then we could ask things like, is there significant enough correlation to use the trend lines equation? Why or why not? All of these things are much deeper and ask much more of students than we did before. We're getting past the skill level and expecting more with comprehension and analysis and application of the concepts. So we're going to move from questions that ask students how to do things, because those questions, if you just ask them how to do something, they can be completed with technology. Things like Google or Photomath, Wolfram Alpha, whatever, they can be completed using with some form of technology. So if we want to get away from that, we need to move into questions that are asking things like what, where, when, why. Instead of just computation, we're asking students to make decisions. So keep that in your mind when you're trying to rewrite a problem into something that can't be easily Googled or done by some kind of electronic program. Are we asking students to just compute something, or are we asking them to make a decision? Because when we ask them to make a decision, we're asking more of them, but it's also something that's more likely going to be something that only the human brain can do and not so much just technology. So one thing to keep in mind when you are working on rewriting problems to become something that's non-Googleable is that you need to write something that is a problem as opposed to just an exercise. And a lot of the things that we ask students to do are at the exercise level. An easy way to think of it is this something I could type into Google or Photomath and it would give me the result? If it is, it's probably an exercise. If it's something that requires more thought and understanding, and probably you can't just type it straight into one of these programs, it's probably a problem. Now, that's not the only definition of this, but exercises are something that's more formulaic, something that's more algorithmic, and it is easier to program technology to be able to solve them for us. Whereas problems require original thinking to be able to actually solve them. This is what we want to be aiming for when we are providing non-Googleable problems to students. So things like, for which salaries is option A better than option B? And you give them two options, a 5% raise or a 3% raise plus $1,000. That's a much more involved problem than the exercise of solve this system. Also, it's a whole lot more motivating and interesting to students. So there's, on a lot of levels, there's bonuses to this. It might seem like extra work at first, but there's a ton of benefits to moving to things that are what I call non-Googleable. Okay, so what we're going to do now is we're going to move into some examples. I'm going to show you some problems from a couple different courses. We're going to start with beginning algebra and a topic that we do a lot of, which is solving linear equations that are in one variable. And we're going to look at how could we rewrite it to be something that is non-Googleable. So here's a simple, solve the equation 1.5x equals 35. Clearly we can put this into photomath and it will be able to spit out an answer for us really, really quickly. So one technique that you can use to rewrite it is, instead of trying just to write what I call almost like naked algebra, there's no context whatsoever, is try to write something that requires authenticity and context, but it would also involve solving linear equations, but it does not appear to at first glance. So here's a problem that I love, and this is a true problem. It came from when I was watching an episode of Shark Tank. A business owner offers, I kid you not, 3.14% of his company, Pavlok. Go Google this if you'd like to watch this episode and watch him be, the guy was eviscerated by Mr. Wonderful. But he offered 3.14% of his company for $500,000. So what value is he placing on his company? You're only getting about 3% of it and you have to pay $500,000. So how much does he actually think it's worth? So, and Kevin, Mr. Wonderful, he quickly figured it out. But this is a great problem for students to solve. And they often just try to take 3.14% of the number of 500,000. They don't get the right answer and they're wondering what they're doing. And then they start just playing around with different ways to use their calculator. Do I multiply these two? Do I divide these two? What do I do? If you write an equation, if you write a one-step linear equation, you can solve this problem very, very quickly. So this is a great use of one-step linear equations. Another technique is that you can, again, use authenticity and context, but not make it a closed problem where it has a solution, but instead an open-ended problem that can have multiple right answers. This is a technique I use often. In this case, we could say, find 3 Shark Tank pitches online. For each, write the percentage equity offered, the amount of money requested, and the resulting value of the company. Show how the value of the company is calculated. That is much more demanding of students. It requires them to go find things. It's much more difficult to copy or cheat because they're supposed to go find these pitches, and there's hundreds of pitches to choose from. So, if 2 students come up with the same 3, we're going to know they work together. But this is a great thing that will ask more of students. And again, you can get at the idea of solving linear equations with this. So it basically takes the previous situation I had with Pavlok and pushes it one step further because it's actually now open-ended, and they're going to do this on multiple situations, not just the 3.14% and $500,000. Another technique is, let's say you don't want to go into context. You can say non-contextualized. So you could state, like this 1.5x equals 35 has no context. Okay, so we could stay in something like this. And one of my favorite techniques to use is create an equation such that. Okay, so we're not asking them to create a problem in a real situation, although you can do that. Instead, we're asking them to create an equation. So what you could say is create an equation that would be solved by dividing by 2 and adding 1. That is not something that you can put into photomath. It's much, much, much more involved, and it's a great problem. It's going to demand more of students because, again, if you look at 1.5x equals 35, there's a lot of students that can solve that without even thinking, and they don't really know what it is they're doing. They don't know what they found when they're done. They just know divide both sides by 1.5. Asking them to create an equation that could be solved by doing a certain number of steps, that is going to demand more understanding from them. So it's not only something that they can't just put into a program, but it's also demanding more of their understanding. Now let's look at a pre-calculus situation of graphing trigonometric functions. So a classic problem might be graph the function y equals 2 cosine x minus 1. And granted, with graphing calculators, something that we've used for decades now at this point, it's definitely something that we don't ask as much of because the graphing calculator can do this. So you've had practice probably at this idea of rewriting a problem for it to be a richer problem that is not so skill-based and not something that they can just plug into a program or a calculator. So here's some ways that we can do that. This can be really challenging and demand a lot of students. And the technique is state the characteristics. So you could say for the function y equals 2 cosine x minus 1, state 8 characteristics of the graph of the function. They're going to be able to rattle off some simple ones very quickly that, that it might be a smooth curve, continuous, the amplitude. There's certain things they'll be able to say very quickly. If you only ask them to do 2 or 3 traits, then having the graphing calculator would be enough to just find the result that they're looking for in this case. When you ask them to state something like 5 or 6 or 8, that's going to push them that they have to have a greater understanding of how the function works, and being able just to read it off is not enough. And you can make limitations on this. You can say you cannot list more than one ordered pair that is on the function, because one trait could be that the function's graph contains such and such point. You could limit it and say that you can only have one ordered pair. Whatever you need to do, but you can make this so that students have to dig deeper to be able to give you more information about this function, which is the whole goal of what we're trying to get them to understand. It's not just, can you make a table and plot points? The calculator can do that. It's, do you understand what you have in front of you once you've created it? And one more technique, you can also, just like we had create an equation that does this, you can also create a function such that blah, 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 and you can give some situations. So you could say, create a trigonometric function in 2 variables such that the following characteristics exist in its graph. The period is pi over 2 is a 0, and its domain is all real numbers. If you ask students to do this, again, you're demanding much more of them. You're still going to be getting at the idea of a graph of a trigonometric function. But now we're saying, here are its traits, go build the function such that these things are true. That is going to demand more of them. And there's more than one right answer in this case. So again, it provides an open-ended situation, and it's not as easy just to cheat. Again, my name is Kathleen Almy, and if you'd like to contact me, my email address is kalmy@almyeducation.com. Thank you.